All right, hi guys. We're going to look at compound interest, but really what we're looking at is something more general than that. I'm just going to use interest as a way to get into this idea. It's an extension of some of the stuff we've done with the exponential functions. So let me just start with an example. So let's imagine we're investing $100, right? And let's just make things simple and say we're getting let me just see what I did, 10% per a year, right? Which is would be a lovely rate to get if that was true. So at 10% per year, right? So if we wanted to know how much we would have after 1 year, so I'll say after 1 year, we would start with our original 100 plus we get 100 times 10%, or put units at the end, $110 in total, right? Because 10% of 100 is 10, and so we've added that together. So one of the things that often happens when we invest is this is called compounding. This would be compounding annually. Once per year, you get your interest paid. But let's now consider the case where we compound more frequently. Let's just take a simple case where we still get our $100 at 10% per year, but we could compound it. I'll say n equals 2, right? N is going to be a number or a letter we often use to represent how often we're compounding it. So I'll just start using it here. So this is going to be the case where n equals 1. Now we're looking at n equals 2. So what that means is that twice during the year, you're going to get your interest. But because you're supposed to get a total of 10% per year, you don't get the full 10% each time. You get half of it. So halfway through the year, you get 5%, and halfway through the year, at the end of the year, you get the other 5%. But it doesn't mean you end up with the exact same amount of money, because let me just let's make this clear. At 6 months, we've got our original $100, and we're going to add to that. We'll take our 100, and we'll get half of 10%, right? Which is 5%, but let's just write it out to be clear. There's our 10%, and we're dividing it by 2. So you end up with 100 plus 5% of 100, or 5, is $105. Sorry, I'm being sloppy with my dollar signs. I'm going to just kind of save them for the end, just so that it makes these computations easier to look at. So now we still are owed 5% more. So at the end of the year, at 12 months, we're going to compound again. However, now we have $105. So we take that 105 and we add to it 5% of 105, right? So we have our 105 plus, but 5% of 105 is bigger than 5% of 100. 5% of 105 is 5 1/4. And that makes our grand total 110. I'm being terrible with these dollar signs. $110.25. Okay, so if you notice, right? I mean, we started out getting 10% at the end of the year. We had 110. Here we're getting a little more than 110, right? A quarter's not a lot, but these kinds of differences add up over time. Let's make sure we understand why that happened. It's because we got that first $5 a little early, and then that $5 started earning interest, right? Here, in this first case, only the $100 is earning interest during the year, and at the end of the year, we get $10. In that second year, that $10 will start earning interest. So if we continued this one to the next year, right? If we took 10% of $110, it's now $11. So you do get more that second year, right? Well, here that kind of compounding happened earlier. We got that $5 halfway through the year, and immediately that $5 starts to earn interest. And the amount of interest that $5 earned is the difference. That extra quarter we got came from that $5, right? And so then the next year, when in case one we earned $11, we'll earn more than that, right? We'll earn a little bit more than that. And so each year you're getting a little bit more, and those differences add up over time. Okay. So let's look at how this, let's work out how this, what this formula looks like more generally, right? So we don't have to go through this computation each time. So for example, let's say we're going to invest P dollars, using P to be the amount, dollars at R percent, right? So R is our percentage as a decimal, right? So let's just call it R is the, let's just call it the rate. At a rate of R, let's say it that way, a rate R per year, compounded N times, okay? And T is going to be the number of years that we invest for. Okay? Let's just imagine what's going to happen. So we start at T equals 0, and we will have P dollars. That's our, we walk in, we hand them our amount of money that we want to invest, and we have P dollars. Now, during the first year, right, depending on the size of N, right, we did N equals 2 here, so if N equals 2, there's one halfway through the year and then at the end of the year. If N was equal to 3, we'd 3 times during the year, so every 4 months. If N was equal to 12, you'd be doing this every month, right? And each time you at each compounding, you're going to take your original and you're going to add your original times. Let's look at what we did over here. We had to take our interest rate and divide it by how many times per year we were getting our interest. So in this case, it's going to be R divided by N. Okay. And so what we will end up with is, let's factor out a P, and we get 1 plus R over N. Okay. So this is at our first compounding moment. Okay. You can in your head say, let's say monthly. So I want to keep this general, but if you need to imagine something, you could say this is after month 1. So N would be 12 here. At the end of the first month, this would now be how much we had, the original plus the little bit of interest we earned. The next month, or whatever the period is, we would start, we have this amount, right? That's how much we ended with last time. Just like here, after getting that $5, the next time we compound interest, we start with that $105. And we're going to take that amount and multiply it by that little bit of interest we got again, right? That's what's happening right here. We took that same amount and then multiplied it by the 10% divided by 2. In this case, it's maybe 10% divided by 12 or 5% divided by 6, whatever the rate is and whatever N is, right? Let's do a little algebra and factor out this P times 1 plus R over N. All right, I'm going to make this really clear. So we're factoring out this factor, and what's left, when we factor it out from the first term, we have a 1. When we factor it out from the second term, all that's left is that R over N. We get the same thing again, which we can write as 1 plus R over N squared. Okay. Well, this little pattern is going to keep showing up. If I do this again for the next month, let's go ahead and just do it. Here's how much we start at the next compounding period with, squared, and we take that 1 plus R over N squared, and we multiply it by our interest rate. Then we can factor out 1 plus R over N squared this time. What will be left is 1 plus R over N, and the new total amount will be 1 plus R over N cubed. Well, you can keep doing this until, for each year, right? If we're, or if yeah, let's just go with T as years. If there's N times during the year, you can do this N times to get P is 1 plus R over N. Sorry, my N looks like an R there. To the N, right? And this would be the amount we have when T equals 1. Okay. If you did it again for another year, I'm going to skip all the intermediary terms, but we're going to keep doing this. At t equals 2, you'd have p times 1 plus r over n to the n times 2. And if you did it for a third year, you'd have n times 3. So in general, for the general after t years, let's say it this way, after t years, we will have p times 1 plus r over n to the nt. Okay, this is, I'm just going to give this a name. This is a function, right? So if you know, what you would have to know is how much you invest, p, the rate of interest, that's our r as a decimal, and how many times per year that's compounded. That would be n, and then t is the number of years, right? T could also be something like number of t could be in months, and then you'd be like how many times you're compounding per month. So if you've got a monthly interest rate um, and compounded daily, you could do it that way, and it would tell you how much you have after t months. For investing, it's typically years, but there's other things that this formula will apply to. Anything that has what we call exponential growth. And this is that's compounded in this way. Now, if you understood this derivation, that's great. I think at this point, understanding this formula and how to use the different pieces in it is what's crucial, and you can kind of go back through and play with those numbers to see how we get, or play with those symbols to see how we get there. Because really, we're actually going to move from this to something even more important in a second. We're ultimately going to land at a very fundamental and important formula. So let's do a little bit of algebra here. So I'm going to take this formula, a of t is equal to p times 1 plus r over n to the nt. There's a few different ways to derive this. What I'm going to do is just take the symbol. I'm going to let k equal n over r. Right? It's a little confusing to understand why I'm doing this, but it's just to play algebraically. Okay. So if I do that, well, if k is n over r, then r over n is 1 over k. Right? And this is r over n. It's just the reciprocal. Right? And if k is n over r, this is equivalent to saying n equals r times k. Right? Just multiplying r over. We're assuming r is not 0. And so that means I can replace this n in the exponent with r times k. So now I'm going to have, or actually I'm going to write it as k times r. And we still have our t there. Okay. Now I'm going to play with the rules of exponents. When we have something like, if I have a to the mn, I'll just remind you this is the same as a to the m to the n. And so I can rewrite this term here. I'm going to write 1 plus 1 over k to the k, and all of that to the RT, right? I'm just using this rule of exponents, that when you have things multiplied, when you have exponents that are multiplied, you can think of applying one exponent first and then the other exponent. So in this case, I'm thinking of I apply the k exponent first and then the RT, okay? Now, the reason we did this is because I want to look at this term in here, okay? This term, 1 plus 1 over k to the k. I want to think about what happens now. Remember, we're talking about n was compounding interest. How often do you get your interest? Okay. Well, we kind of imagined monthly. You could imagine daily. You could imagine interest compounding every second. Ultimately, we can push to the extreme here of always compounding. You're constantly growing, and the growth is then part of the next growth. Okay. And we noticed that when we went from compounding once per year up here to twice per year up here, the amount we got was more. right? This holds as we keep compounding more and more times per year, because the earlier you get your first bit of money, the earlier it can start getting interest, right? But it doesn't just grow without bound, right? So we're now going to the extreme of constantly, continuously compounding. And it turns out that as n gets larger, so the symbol I'll write is as n goes to infinity, right? The number of compounding periods grows. That will mean as n goes to infinity, k goes to infinity, right? Because k is defined as just n over r. And as k goes to infinity, this collection of symbols, 1 plus 1 over k to the k, if you take the number 10 for k, and then you take the number 100 for k, and you take the number 1,000 for k, and you take the number 1,000,000 for k, you keep putting in larger and larger k values. What we'll find is this gets closer and closer to a certain number, which has an infinite string of decimals. Right? Has an infinite string of decimals. I'm just going to write the first two of them, 2.71, and it just keeps going on forever, right? This number is so fundamental, though, that we give it a special name, just like we've named pi. This is the number E, okay? Euler's number. And it shows up, this is one of the places it shows up when we're talking about how things grow, when they grow exponentially, and lots of things will turn out to grow this way. Lots of investment is done this way, but populations can be modeled this way. We'll see some other things in just a moment. But it shows up in a lot of places, so it's pretty vital, which is why we give it a special name. And so when we compound continuously, in other words, we're letting n grow without bound, we're constantly compounding our interest or whatever it is, we arrive at this formula. P, and I'm going to replace this 1 plus 1 over k to the k because we're letting n grow without bound. We get our e here, and we have that exponent of rt. So we're replacing that symbol in there with this number, this very, very important number e. And then we have the units, or the exponent of rt, right? P still represents how much we're starting with. R is the growth rate, and T is how many units of time, right? Typically years, but it can be months or whatever else. Whatever the time unit of time of interest, right? So for example, if we invest $1,000, earning 10% continuously, compounded continuously, then the amount we would have, well, then the amount we would have after t years is given by p e to the 0.1, there's our 10% t. And if we wanted to compute something like how much is in this account after 3 years, we'd have our $1,000 for p e to the 0.1 times 3, which you can throw into a calculator. And I got 1349 and 86 cents. Okay. And this would hold if this kind of growth is a good model for lots of things. So for instance, I could redo this problem and say a scientist has 1,000 bacteria with a growth rate of 10%. How many are there after 3 years? 10% per year, we would say A of 3 is 1,000. We would do the same computation, only now we'd be talking about individual bacteria, so we'd probably I would probably just round down, right? Just depends on what you're doing. Although 1350 is a nice round number. Let's not worry about that little detail, right? It's telling us the same thing, right? This is a model. Our mathematical models are never exact anyways, and so or seldom exact anyways, and so we're just getting a good prediction for how many bacteria we'd have after a while. One more thing I want to add into this. Um, this is also a good model for what we call exponential decay. And so what happens in exponential decay is we just have a negative rate. So for example, let's say we have radon 222, and we know it decays at a continuous rate of 17.3% per day. We want to know how much of 100 milligrams is left after 3 days. So we start with 100 milligrams, and we want to know how much we'll have in 3 days. The same formula applies, A of t. We're going to have our 100 milligrams, e to the, but now we have negative. Oops. Negative 0.173 t. And if we wanted to know how much after 3 days, we plug in our 3, negative 0.173 times 3, and I got approximately 59.5. What were we in? Milligrams, did I say? Yeah, milligrams. All right, and so this will describe exponential decay as well as exponential growth. Okay. And we can see why this would be important, right? If you had some amount of material, you need to do an experiment and it's rapidly disappearing, you need to know how long until you don't have enough to do your experiment or whatever it is, right? That you would need to know this. Okay, that is it for this example. The big takeaway is this exponential growth formula, right? For continuous growth or decay. Right? That tells us how much of something do we have after t units of time when it undergoes continuous growth or continuous exponential growth or decay. So this is something that we're going to burn into our brains. Okay, that is it for this one. Thanks, everybody.